I have the pleasure to present a method we propose to efficiently detect vertical objects in high-quality point clouds of construction sites. A global survey of the Co.KG revealed that even more than safety, cost, and quality, adherence to the project schedule is the most critical performance measure in the construction industry. Despite that, still more than 50% of typical construction projects finish behind schedule and with cost overruns. One of the main reasons of this problem is that monitoring progress is still mostly performed manually, but yields that the delays are not recognized on time. Usually in a construction site you have a schedule plan in 2D, the one taking pictures all around the construction site and monitoring the progress manually on floor plans. This is labor-intensive and non-comprehensive. In order to address this problem, many ideas have emerged. One of the most promising ones is the one proposed by Mr. Braun, in which a 4D building information model that not only has the geometric information but also the time information is compared against a point cloud of a construction site. So basically, if you overlay the point cloud and the 4D building information model, you can see if the project is ahead or behind the schedule. But there is still a main challenge with this approach, and is the presence of temporary objects, and that makes difficult a reliable automatic progress tracking. In this case, there are, for example, the scaffold and formwork elements. Therefore, the objective of this research is to detect vertical instances of crane, scaffold, and formwork elements in point clouds of construction sites. The method we propose can be divided in three main parts. First of all, a pre-processing that takes as input large-scale TLS point clouds. Second, there is a crane and scaffold detection. And finally, formwork detection, giving us an output, the semantically enriched point cloud. In the pre-processing step, the point cloud is downsampled, and it is also rotated so that it is aligned with the X and Y axis. To do this rotation, the point cloud is projected into 2D. The probabilistic Hopf transform is used to detect straight edges, and K-means is used over the angles of the straight edges to find the corresponding angle of rotation, which allow us to align the point cloud with the X and Y axis. In order to detect our target elements, we apply a step that is called regions of interest separation. In this case, for example, we want to separate the regions that may contain walls. To do so, we project the point cloud in a grayscale image. We then apply a height threshold and a dilation morphological operation, which will join elements that are close to each other, in this case, two faces of the wall, for example. And then we apply a threshold by blob size, separating only large blobs that may conform mostly wall elements. If we apply this method in such a point cloud and apply the final mask to filter this point cloud, we obtain this result, in which we have mostly formwork and wall elements. We can do a similar procedure to separate regions that may contain cranes. To do so, we then apply thresholds to separate tiny and height elements. We get these results. And subsequently, in order to detect cranes and scaffold, we detect 3D contours in this point cloud. To do so, we apply the method proposed by Lu, in which the point cloud is separated into regions with the region Braun algorithm. Then these regions are projected into 2D. Then the least square fitting algorithm is used to detect lines. and these lines are finally then projected back in 3D. Once we have these lines, we merge in if they are enough close to each other, and we apply also a minimum length threshold. Then we look for a specific pattern in these 3D vertical lines. For example, for crane and for scaffold elements, we have always these 4 vertical elements with a specific distance in between. Similarly happens for the scaffold element and its uprights of a certain distance in between. If you look into the literature and the regulations, these are the standard dimensions for the cranes and scaffold elements. Once we have found these 4 elements, we create then cross sections in between them, and in each of these cross sections we verify that there is a line that occupies at least 80% of the width of the image. As you can see, cranes and as well as scaffold elements have always a horizontal line in this cross section. In order to detect formwork elements, we applied similar procedure to separate regions of interest. Then we separate vertical and horizontal blobs, which allow us to separate Manhattan world formwork elements from the point cloud. We then create cross sections in these blobs, in this case also with depth information in order to take advantage of the different structure of formwork elements. These cross sections are then classified with a neural network. For that we use the PyTorch C++ front end, the AlexNet architecture, and we create a training dataset with the dataset number 1, and we achieve a 93% of accuracy. Here you can see a small subset of training dataset. They are formwork elements and non-formwork elements. Those are the results of our method in 3 datasets. We achieve an overall precision of over 88%. We detect correctly the crane mass in all datasets. However, it doesn't mean that the method will always detect crane mass. For example, if there are banners in the crane mass, it won't be detected by the method. For scaffold and formwork detection, we have mainly problems in dataset number 2, which I will discuss in the following slides. Those are the results for dataset number 1. Here you can see in green the crane mass, in blue the scaffold elements, and in red the formwork elements. Here are the results for dataset number 2. Here this dataset doesn't have color information, but still the method is applicable because we don't require color. And those are the results for dataset number 3, where we have a lot of scaffold elements in the surroundings of the construction site. Regarding the scaffold detection, we probably detect this stacking pallet element as a scaffold element because it has these vertical elements with specific distances between us the scaffold elements, and also has this horizontal line in its cross section. We also have problems with occlusions. If at least one of the uprights of the scaffold elements is occluded, the element is not detected by our method. Those are some results for formwork detection. As you can see, the neural network sometimes detects other elements as formwork elements. We also have problems because if the cross section contains other elements besides formwork elements, they are also classified as formwork elements. In this case, for example, these windows parapets and this person here. And again, occlusions, for example, in foundation formwork, cause heavily problems to detect these elements. The method took in average 20 minutes to process each of these datasets. It is 1 second to process 100,000 points. And when we analyze every step of the pipeline, we see that the cross-section validation takes the longest time in dataset number 2. This is because in this dataset, we have a lot of props for the slab formwork that may have this pattern in these 4 vertical lines, similar to cranes and the scaffold. Therefore, the method has to generate many cross sections and verify that there is a horizontal line on them. We compare qualitatively our method with other state-of-the-art methods that detect scaffold elements. For example, the method proposed by Tsu can only detect the scaffold elements that are next to a facade. We don't have this limitation. Their method also can only detect scaffold elements with a pay width of 0.8 meters. We can detect scaffold elements with a large variety of dimensions. We can also apply the method in large-scale point clouds, which is not the case with the method proposed by Wang. However, our method is not applicable in low-quality point clouds and cannot detect all the parts of the scaffold elements and create a 3D model of them. Nonetheless, our method can detect grains and formwork elements. Those are some of our references. Thank you for your attention, and if you have any questions, please reach me out.